Special relativity is a theory developed by the well-famed Albert Einstein to describe and explain the behavior of things that happen close to the speed of light. It's called special relativity because, again, it only applies to very specific situations where the different reference points are not accelerating. Special relativity is based on two postulates. 1. The laws of physics are the same in all inertial reference frames. The second postulate states that the speed of light is the same for all observers in a vacuum, regardless of their motion relative to the light source, about 300 million meters per second. Special relativity applies to inertial reference frames, or non-accelerating frames. That is to say, in special relativity, people are either stationary or they're moving at constant velocity. Okay, wait, what? It's okay if you get a little confused. Let's take a look at the following example. Say Aton is waiting for Tyler to arrive on a hypothetical train traveling at 1/4 the speed of light. Oh, and the front of the train has a headlight too. From Tyler's perspective, the headlight is moving away from him at the speed of light, and he is moving at 1/4 of the speed of light, or 0.25 c. You'd think that from Aton's perspective, and based off classical relativity, it would look like the headlight is traveling at 1 1/4 times the speed of light, because of its own speed plus the speed of the train. Well, that's incorrect, and that is because light always has to move at the same speed. Because you see, it is impossible to move faster than the speed of light. So basically, from Aton's perspective, the light would not be traveling at 1 1/4 the times the speed of light. It would look like it is moving at exactly the speed of light. Again, what? Now, I know this sounds strange and very counterintuitive, but this is where we begin our lesson on special relativity. Let's take another look at the train example. The second postulate in special relativity states that the speed of light in a vacuum is the same for all observers, about 300 million meters per second, whether or not the light source is moving. So even if light coming from a train moving at 1/4 the speed of light, the light itself is still moving at the speed of light. Obviously, this doesn't make any sense, but let's take a look at the equation for velocity. Velocity is equal to distance over time, and we know that special relativity tells us that for light, its speed is always constant, which means that two other things must change to account for this: time and distance. When time changes, it's called time dilation, and when distance changes, it's called length contraction. We'll talk about length contraction another time, but for now, we're going to focus on time dilation. Time dilation occurs when another reference frame is moving relative to you, so time in that reference frame slows down relative to the time you measure. Let's take a look back at Tyler and Aton. Let's say Tyler has a mirror with him attached to the train, 5 meters away from him. Tyler has a flashlight and shines his flashlight towards the mirror, which reflects the light back towards him. From Tyler's point of view, it's very simple. The beam of light traveled 10 meters there and back at the speed of light. But Aton, looking through the window, saw differently. Sure, he saw the light traveling to the mirror and back, but the train was still moving. While the light was traveling towards the mirror moved sideways relative to Aton's spot on the platform. And when it was moving back towards Tyler, Tyler moved even more sideways. This would cause the beam to move diagonally, as though its path formed two sides of a triangle. From Aton's point of view, the light traveled a greater distance than Tyler's point of view, but special relativity tells us that light's speed was still exactly c, even though it traveled a greater distance. Therefore, if the light traveled a greater distance at the same speed, it must have been traveling for longer. Basically, from Aton's perspective, time slowed down for Tyler. That's time dilation. If you measure the distance the light was traveling from Aton's perspective on the platform, you calculate that time slowed down for Tyler by a factor of 1 divided by the square root of 1 minus the train's velocity squared divided by the speed of light squared. We call this factor gamma, and it applies to any situation where another inertial reference frame is moving relative to yours. Gamma will always be greater than 1. Time in that moving reference frame will seem to equal time in your reference frame multiplied by gamma, and thanks to this, we can make many formulas using gamma and time. All this sounds counterintuitive and weird, but that's only because we're used to seeing our world at much slower speeds than light. This only proves that our gigantic, expanding universe is indeed a very strange place when it comes to light speed. Thank you so much for watching. They call me Matthew the Physics God, and I'll see you in the next episode. Peace.